Next unit is on, okay? So we already got unit 1 down. That was a big, huge review unit. A couple of new concepts with like the mass spectrum, and then the combustion analysis, but a lot of it was related to like isotopes and other things that we knew. This unit is very similar. It's a lot of review, but we're going to have some different applications of it, some things that might be more advanced. So in this first, the first couple of slides I actually printed for you, so you guys can get your space. This right here is what we're going to kind of go off of, and I think a lot of this will be what you read about in the book and or did on the active reading guide, so that you can take minimal notes, but I wanted to print this for you so that you can have some of the images and some of the ways that I explain things so you can memorize. I'm going to have you hold on to that until we're at the end of class. Okay. So what are some of the key words or key concepts you read about? Shout them out. Acid-base titration. So we are going to be doing another acid-base titration at the end of this year. That's what investigation 4 is. Tell me more. What else did you read about? Polarity, molarity. What else? Ionization. Solutions, dilutions, dissolving, dissociation. All these terms, right? The terms do mean different things, and we're going to emphasize that today so that you use them in the correct way. This is something Nathaniel got scared about. No, you do not have to know every single one of these, but what you need to know is that different transition metals, as you can see across the board, have different charges, and along with these different charges, they have different what? Colors, right? Transition metals give color to a solution or to a compound, generally because they have inner d electrons that are able to move in different ways. As the d electrons move up and down, they emit a certain wavelength of light, like your gemstones from the very first day whenever we were talking about gemstone chemistry. So that's just a quick point, and I'm not going to go through all the warm-ups that I have here. I'm going to make sure that we have some time for practice today. There we go. Okay. So here's what I want to do. I will give you guys back your test after my 2 girls take theirs. If you did not do well in the Unit 1 test, you have to come back during teal to do some corrections, and I will use that as an extra grade for you, not as a test correction grade, but as a quiz grade. And I usually have everybody do it, but I'm going to say if you made below a 90, you have to do it. This test should have been a 90 plus test. It was just timely you had to work on, timeliness. Okay, so in this particular example, we're going to talk about aqueous solutions, so that means dissolved in water. This is on your notes if you want to take down any extra things. I'm going to write down some extra things here too. I just did that for ease of listening. But if you're an active learner, then you'll be writing and highlighting and adding additional comments and stuff like that. So that way you're not zoning out on me, because I do the same thing. I was in class for 10 hours on Saturday for my grad school, so let's just, I know what it's like to be there, bored to tears. Okay, so polar covalent bonds. What is a polar covalent bond specifically? Anybody? Thank you. Unshared, a covalent bond with unequally shared what? Okay, so in this particular example, H and O, who is more, has a greater share of the electrons? Why oxygen? Because it has to reach octet. That is true, but hydrogen has to reach duet, right? So they're sharing because they have to share electrons, because they both want to reach 2 electrons or 8 electrons. But why is it sharing more? Why is it pulling them more? What's the term for that? Anybody from my class? No? Well, kind of. What's this one from periodic trends? Thank you. This one has a greater electronegativity. And if you have or electron negativity is sometimes how it's said. If you have a greater electronegativity, you desire the electrons more. You pull them closer to you because your nucleus has a higher effective nuclear charge. And we're going to go into that in great detail, like in the spring, like March. So we're going to hit it just a little bit right now. Whenever that happens in a particular molecule, on a bond, it creates this thing called a dipole moment. Dipole moment always points towards the more electronegative one, leaves the hash mark, which kind of looks like a plus, is on the less electronegative one, leaving us overall with a partial negative and a partial positive charge around the atom, around the molecule. So the partial negative right there is partially negative because it's not a full negative. Why is it not a full negative? Because is the oxygen really taking the entire electron? No, it's taking part of it. It's not dividing it up. It's just sharing it as an overshared component of it. Okay, so this characteristic, this physical property about water, allows it to dissolve a lot of things. Dissolve, though, is a really weak term. Dissolve does not really indicate what's happening in terms of the chemistry. Dissociate, dissolve, ionize are going to be three terms we need to differentiate between. So I say dissolves up front because this is a layman's term. Okay, this is layman's term of what water does to other stuff. But anything that's polar means it interacts well with water because they have kind of like north and south pole ends, they have opposite ends. Anything that's ionic definitely interacts well with water because that's like the epitome of a north and south end, like a positive and a negative ion. So that's why they work really, really well together. Even things with an alcohol group work well to dissolve or interact with water because they have a component or a portion of their molecule that is polar. So if you're looking at, this is, you might have to redraw it, might be really small on yours. This is ethanol. Okay, ethanol has a hydroxyl, okay, or an alcohol group, OH group on the bottom side of it here, and that is going to be making it slightly polar. Slightly polar, because this oxygen here is a slight positive. This oxygen here has a slight negative. The rest of it's kind of neutral-ish, but this area here will interact well with water. This H right here interacts with what part of water though? Oxygen. Right, so this oxygen has what on the bottom side actually in this picture? What are remaining there that are not depicted? Lone pairs, right? 2 lone pairs. Okay, so this hydrogen here interacts, and those lines mean interacts or attraction, interacts with the lone pair. What can that water then do to the H? Possibly. Can it attract it a lot? Yeah? Can it attract it so much that it pulls the H off of this molecule? I'm telling you it can. It really can. It's very, for alcohols it's kind of uncommon, but for acids it's extremely common, and that's why acids are really, really acidic, have a low pH, because they make a lot of H pluses in solutions. It pulls the H off of this molecule, this other molecule. So this right here, this green stuff is, what am I depicting here? What force? It's an electrostatic attraction, but there's 3 forces, IMS, that we know about. London dispersion, dipole-dipole, and hydrogen bonding. Which am I depicting here? Hydrogen bonding. Okay, hydrogen bonding is a flat lie. It is not a bond, right? What is it? It's more of an attraction, okay? It's not a bond whatsoever. So that word hydrogen bond, I wish I could change it, but I can't. I don't have that kind of power yet, but I'm working on it, guys, because it's a big fat lie. So here's another depiction of the same thing. If you had to label something as image, and they had this almost this exact example last year or the year before an exam, they ask you to label 2 bonds, a polar covalent bond and a hydrogen bond. Where would a polar covalent bond be?
Carbon between C's.
Not polar. This would be a non-polar covalent bond, actually, because it is here. Is that what you're talking about? That one has no differences in electronegativity because it's carbon and carbon. Give me more. So the C and H here, it's probably non-polar covalent too, because the carbon and hydrogen don't have a huge difference in their electronegativity. Thank you. The C and the O probably has a polar covalent bond. This one definitely, between the O and the H, definitely has a polar covalent bond. And then this right here, again, is what? Hydrogen bond. Not Victorin or whatever that is. Okay, so we need to be able to identify those from a picture, and I think we got that here. Oh, what can hydrogen bonds form between? We kind of just told a little bit about it. What was it forming between? Say again, Clayton. Okay, so something with a molecule with a hydrogen and a molecule with an oxygen, right? What else can it form between? Okay, hydrogen and, so a molecule with a hydrogen and a separate molecule with an oxygen or fluorine. What else? There's one more. Nitrogen, good. So a hydrogen with a nitrogen. So if you were a molecule that has an OH bond, an HF bond, or a NH bond, and another molecule with an OH, NH, or FH, whichever order, your molecule can interact with another molecule because you have such polar covalent bonds within yourself. You overall become very polarized. So you can interact with other very, very polarized molecules. So another example would be with, what's this called? NH3? Ammonia and another ammonia, or an ammonia with another water. So it's always about the interaction between those things, and that's how things dissolve in water. That's how things dissolve in other solvents other than water too, but specifically we're talking about water this round. Okay, this is on your sheet. We've heard the word polyhydration. When we think hydration, we think water. We've also heard of like copper 2 sulfate pentahydrate, right? What does that mean? Within the crystals, right? So the word hydrate means water, H2O. Whenever a salt, like something that's ionically bound, ionic salt, whenever it dissolves in water, it doesn't do it easily because ionic bonds are really strong or really weak.
Really strong.
Really, really strong, right? The electrostatic attractions between a cation and an anion are huge. They're really strong. So what is water's job here? Water's job, when it's hydrating a salt, is to simply attack the ionic compound so strongly that it forces it apart, right? So that means water interaction with the ionic substance is stronger than the ionic attraction for itself. Does that make sense? Okay, so if water's attack wasn't strong enough, its attraction wasn't strong enough, what would that mean for the ionic solid? So it would stay the same. It would be insoluble, right? That's how our solubility rules come into play, okay? So solubility rules like lead, mercury, silver, some of those other things, we're going to learn some more about those in our video tonight. Yeah. You'll see that things are going to be precipitating just simply because water is not strong enough to interact with it. So there's a word for this water interaction. It's called ion dipole attraction. Okay? This is what water is doing. Water has a dipole moment, yeah? It is attracting to ions. If that is stronger than the ionic attractive forces, water wins, the thing gets solubilized, or gets dissolved, or gets dissociated. We're going to use that term appropriately now, okay? So the word dissociated is the word that we use for all ionic salts breaking up. Okay? Anytime you talk about ionic solid breaking up, you say dissociates. So an example of that would be ammonium nitrate dissociating. I use the word dissolve wrong all the time too, just because you don't, in normal conversation, use the word dissociate. Okay, so ammonium nitrate dissociates into ammonium cation and nitrate anion. Now, who's doing this though? Does it just happen by itself? Who's the active player that's separating this? H2O, right? So sometimes you can write H2O above that arrow. Do not write water as a reactant. This was one of these examples was on the exam last year, and you wrote water as a reactant, and then you did not show water in the products. You got the entire thing wrong, even though they understood that water is just a player, but we don't write it there because water itself doesn't change really. So you can write above the arrow, but that's as far as I would go. Okay, so yeah, don't write water as a reactant if you don't have to. And dissociation is breaking apart of ions. We good there so far? Yeah? Just make sure that, like, for example, this equation down here, you see that we have 2 chlorines. So over here you make 2 chloride ions to balance out your equation. And then, what does the word dissolve mean? Dissolve means that you are surrounded by water. Water does not do anything to you. You are just surrounded by it to like kind of be encapsulated so you can go into solution. Not that it's causing ions or it's causing dissociation. So these pictures here, those are dissociations because the sodium ion and the chloride ion have been separated. But what would be a good example of water dissolving something? That would be like sugar. So example, sugar and water. What is sugar? Ionic or covalent? Covalent. So covalent things do not interact through ion dipoles with water. They just get surrounded. And I have a good picture of that in just a second. So another term that we'll use is solvation. Sorry, solvation is one that you need to know, but that's generally because water is solvating things. It's making things go into solution. Let's look at, well, C12H22. O11 is sucrose, and that's one that you'll see with water. Water just kind of surrounds it, like here. I'm not actually drawing the chemical structure out here, but that would be a good example of dissolve versus dissociate. Okay, feel good about that one? Can we move on? I'm talking a lot. Thank you. All right, so here's our ion-dipole interactions again. This is from your book. I'm not going to hang out here very long. This is another example of our dissolving, not dissociating, because you can see that covalent compounds like sucrose, like I said, are just going to be surrounded by water and not dissociate. See? Can I go forward? Yes, thank you. So there's a difference there. Okay, now we get to the word ionization. We use the word ionization really loosely. Anything that ionizes into ions is ionization. But generally, we use the word dissociation for ionic salts and ionization for the ionization of molecular things. Does that really make any sense though? Ionization of molecular things? Molecular things don't have charges, right? So it doesn't make sense to use that way. But that is how chemistry is on this one, okay? I don't have power to change this one either. But you need to know specifically it's for the molecular compounds and how they dissolve. We use the word ionization. So for example, you may have seen this before. Ka is called the acid ionization constant or acid dissociation constant, because like I said, ionization and dissociation are really similar. They're breaking things apart, but one is used for ionic solids and one is used for molecular solids. So, for example, acids, this first acid here is, again, what? Cyanic acid. It can ionize into two species, and that's because all acids act ionic. And that's just how we know they're crisscrossing of charges. But that's how we know a lot about them, is because they act ionically. If they acted molecularly, it's a little harder to discover their properties. So in this one, there's something else I want to tell you here. If I wanted you to show me the dissociation or the ionization reaction for hydrosulfuric acid, what is that compound? H what? 2S. How did you know the two? Crisscross the charges, right? Show me the ionization of that. Good. Okay, so that's the ionization of the acid. The photoionization is something where light causes kind of an ionization of some molecular species. For example, and we have to incorporate a lot of biological and environmental examples in chemistry because they're trying to do more of a cross-curricular kind of feel here. So ozone and ozone can react with each other, okay, by photon ionization. And when photons come into play here, they actually cause electrons to be shifted around to form two free radicals. Okay? And this little dot here means I'm a free radical. What are free radicals? Does anybody know what a free radical is? Radical D? No, that's not. Huh? They do what they want. They actually attack other compounds viciously, and they take their electrons, because this lone dot actually means a lone electron. And so as that lone electron is kind of moving around, it actually steals other electrons from other sources. Sometimes that's really, really bad. If you swallowed a free radical, it would bounce around your insides, and we do this all the time, okay? Our body is always bombarded with free radicals, especially if we have like ozone at the ground level. What's that called? It's like we just had one in Charlotte not too long ago. No, smog is sulfur and some other stuff. It's just like ozone. It's like bad ozone at the ground levels. Like you shouldn't go running and stuff when when we have like a health hazard alert for Charlotte. Anyway, so if you breathe that in, it attacks your insides, right? It oxidizes your insides. What can you do to combat oxidation of your insides? Eat. What combats oxidation? What's opposite of oxidation? Antioxidants? I'm trying to see if you're picking up what I'm putting down there. Okay, apparently not. It's Monday morning at 7:30. Okay, so if you eat a lot of antioxidants, it combats this free radical deterioration of your insides. So any antioxidants in your diet is a good thing. Okay, so far a lot of reviews except for that vocabulary specific stuff. Maybe. You gotta give me some feedback, people. I don't know where you are. Okay, so we know electrolytes are going to be things that are related to electricity, but we generally say that they're electrolytes in aqueous solution. So in aqueous solution, they do what? If we're talking about electricity, what can they do? What's kind of like the definition of electrolyte? Conduct, thank you. They can conduct electricity in aqueous solution. You need to memorize the things that are electrolytes and the things that are non-electrolytes, and the things that are weak electrolytes. There are 3 categories. If you read about this, I know already. So anything that's a strong electrolyte means it will conduct tons of electricity. That probably means it's making a ton of ions. So if you're making a lot of ions, you're probably a salt. That's the first example. And so if I'm let's say I'm a 1-to-1 ratio salt. If I have 1 mole of sodium chloride, how many moles of ions am I making? Moles of ions. You see, I'm making 2 moles of ions because 1 mole of sodium chloride relates to 1 mole of sodium plus 1 mole of chloride ions. So I'm making 2 full moles of ions in solution. Give me something that would make more than 2 moles of ions. Do not use my example here. Give me a bigger, badder salt. Magnesium. That would be like similar here. Give me something more than 3 moles of ions. That's only 2. Magnesium phosphate. Good job, guys. Okay. So, what does that dissolve into? Ions. 3 Mg what? 2 plus and 2 PO4 3 minus. So there's 3 magnesium ions and 2 phosphate ions, because phosphate ions are their own polyatomic ion family. Do not break them up. There'll be a home record, right? So how many moles of ions am I making? 5 moles of ions. So this would be a very strong electrolyte if the phosphate dissolved all the way. We're going to learn about solubility rules a little bit later. Okay, so any salts that are soluble, okay, it's very important that they are soluble, will be strong electrolytes. Any of the 6 strong acids, their definition is that they 100% dissociate. So, strong acids definition, 100% dissociation. What does dissociation mean again? Dissolves or break apart, or it will break apart, not dissolves, right? So you can say ionization or dissociation. We do use those terms more interchangeably than we should, but that's actually how it's read in the book as well. So these 6 strong acids, you have to know them. Okay, close your eyes. There are 3 binary ones. Okay, HCl, what and what? HI, HBr. Stop. Those are the 3 binary ones. All right, look back up here. Look at the ternary ones. Close your eyes. There are 3 ternary ones. Nitric acid, so HNO3. What else? H2SO4, HClO4. So perchloric acid and sulfuric acid. Okay, so you have to know those 3 binaries and those 3 ternaries. That's one of those memorization things that just kind of has to happen. Now, when I draw a single arrow like that, that straightforward arrow, that indicates that it's 100% dissociation or 100% ionization. If I draw an arrow like this, and let's kind of look down here, you see the double-headed arrow? That means it's a reversible reaction. That means it's a weak acid. So I'm going to really do a good job of showing you that, pointing it out to you at the time and then until May. Okay, so if you're at one of the 8 strong bases, you are also going to be, with your hydroxide, 100% pulling apart or 100% ionizing like this, okay? And last year I taught some of you guys how to remember these 8 strong bases. So like Na, OH, KOH, LiOH for rubidium, hydroxide, sesame hydroxide, and so forth. It's a lowercase b on the periodic table. So you see Li, Na, K, Rb, Cs. Those are the 5 that are in group 1. And then Ba, Sr, and Ca are the three that are in group 2A. So it's like a lowercase b if you remember B for base. Got it? That's the little scheme for memorizing. I have to teach myself these stupid things to remember them too, because they're not always easy to remember. Okay, so those are our only examples of strong electrolytes. They 100% make tons and tons of ions. Weak electrolytes don't dissociate well. Okay, they do still make a little bit. So for example, I'm gonna look down all the way down at the ammonia and ammonium example. Whenever ammonia interacts with water, some of it will interact with water to the point where it delivers or achieves a proton or an H+. So that might leave 90% ammonia and 10% product. Only a couple of them will do that. It could be 98 and 2%. I have no idea. To look at this information, I would have to look at something called its KB value, which is related to equilibrium. Some of us are like, equilibrium, I hated that chapter. I hated that unit. But we're gonna learn to love it. It's gonna be our child. We're going to take care of it, even though we don't like it. Okay, it's a distraction, but we have to learn how to appreciate its equilibrium. So this right here is what? Acetic acid. Acetic acid, was it one of those 6? No, so it's weak. So anything that's not on the list of 6 is a weak acid. So give me another example of a weak acid. Okay, so hydrofluoric acid is weak. Give me more. I said nitric acid, nitrous acid. I said perchloric, so chloric, fluorous. So you can see the point. You have to know the 6 hypochlorous. Okay, you have to know 6 strong, and if you do that, you should know everything else that's weak. Okay, so that means that not all of them 100% dissociate. All right, let's continue. Oh, and if you're gonna be working with particulate matter diagrams a bit more this unit. And so what you should be able to do is look at species in a flask or in a beaker or in a titration burette or whatever, and you should be able to indicate if it's strong or weak electrolytes. So if you're looking at that and you see only H pluses and Cl minuses, or if I just said only H plus and X minus, like I'm telling you it's some random ion, you should be able to look at that and tell me it's strong. Why? There's nothing that looks like this together, right? There's no combined compounds. This one you should look at and say, oh, this is definitely weak because what? Right. I see 1 H+, I see lots and lots and lots of other things that are molecular based, that are not ionized off. Okay, so that's how you can look at a picture and tell the same thing. Okay, so I'm actually going to just quickly go down here and then I'll speak back up. Non-electrolytes are things that simply just do not ionize. That makes sense. Yeah. They are not acids, they're not ions, or ionic substances, they're not bases, they're like usually only covalent all the way across. So covalent 100%, very little polarized bonds. It's sometimes hard to tell which ones they are, but for example, ethane, who started their Orgo videos? Not a soul. Okay, so Orgo videos are due on this month, September 24th. They're fun though, okay? You learn a lot more nomenclature and you will become familiar with, like, for example, what ethane is. F means that I have 2 carbons. Ethane means I do 2N plus 2. The N is the number of carbons. So how many hydrogens is this? 6. So C, C, H, 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 H right there. Ethane is 2H6. That's a non-electrolyte. It will not ionize. Okay, so we are going to encounter some bases specifically that are very, very, very insoluble, meaning they're kind of like preservatives. But the little tiny part that actually does go into solution, like this calcium hydroxide, for example, it actually is very, very insoluble. But the part that actually does go into solution, it does dissolve 100%. Why does it dissolve 100%? What did we just talk about for calcium hydroxide? It's a strong base, okay? So this right here, the aqueous portion of calcium hydroxide that does get surrounded by water and dissolved in solution, it 100% ionizes. But you're going to have some of that present, and then you're going to have a ton of some precipitated out calcium hydroxide. So it does the same thing. It both precipitates and dissolves. It's only because it's limited in its solubility. When I say limited in solubility, it has a KSP value that's very low. So you've noticed me, I put K up there 3 times now. K is the equilibrium constant, and it is important for pretty much all reactions. It's important for all dissociations. So I'm going to keep repeating that. But SP in this case means solubility product. So it's talking about if it's soluble or not. And I'll keep emphasizing that just so you can see the difference. And so the reason that we do know that this calcium hydroxide does dissolve is that this solution would be very, very, very basic. So like pH 14, 16. Okay, it's going to be higher than 14 if possible. Okay, we just talked about our strong acids. The only thing that I didn't mention was the diprotic one. We said sulfuric acid, yeah, was one of our 6 strong acids. It has 2 ways that it ionizes. The very first one, and I think I have this written down on the paper, don't I? Yeah. The first one is just one H plus pops off, okay? And you'll notice that my arrow, oh, I didn't write this down. H2SO4, arrow, full arrow, H plus, HSO4, 1 minus. What is this HSO4 one called? What's its name? Say again? Bisulfate or hydrogen sulfate, but bisulfate's more intelligent. Okay, so single arrow indicating it's a strong acid, right? I can also do the same thing with the second one. Draw a double-headed arrow to indicate that it's not a strong acid, it's a weak acid, because that's still an acid. Why? Not simply because of the hydrogen, because the hydrogen can come off. Because it will come off. Like I can have an OH and that's not an acid. SO4, 2 minus. Okay, so that's a weak one because not all of that secondary reaction will occur. Okay, this RCOOH is a functional group called a carboxylic acid. So that word acid again means what? Hydrogen comes off. So this carboxylic acid, I'm going to put in the form of what is this guy? I've drawn it before. So CH3COOH. So this is acetate that's surrounded in red here. C2H3O2, that's acetate. So it's the whole shebang. Acetic acid, right? So that whole thing is acetic acid. Well, why is it called an acid? Because this will pop off because it has the functional group COOH. COOH. You're going to start to see the pieces of a molecule. This is a functional group, and a functional group is an organic chemistry term that indicates this is a group on a huge molecule that is the action part. It's the active part of the molecule. So why is this the active part of the molecule? Because this is the part right here that is making H plus to make it acidic, to make it reactive. So the functional groups come in many varieties. You've got alcohol groups, you've got carboxylic acid groups, you've got amine groups, you've got a lot of groups. And those 2 people who took AP Bio, they're like, yeah, I got this. I know this. So I know you guys are happy about that one. Okay, and that R, AP Bio, what does the R mean? Do you remember that part? Anybody? R means that this part right here can vary. So I can have this functional group COOH. I can have that functional group on 2 carbon chain, 4 carbon chain, 15 carbon chain. That R group is this part back here that can vary. In this case, I just have a CH3 on there. It could be C2H6. It could be a lot of other stuff. Okay, you guys can read through that. I'm not gonna read that. Put a star by it. Read it. Because I want to get to dilutions if I can. Okay, whenever you're writing out your weak and non-electrolytes gases, you write them as molecules, you put a G afterwards. So in this example that we had in our lab last week, ooh, that's really sloppy, but there we go. We had this, NaCl. So sodium bicarbonate plus HCl yields carbonic acid and sodium chloride. What do we do from that? CO2 gas, and H2O. Liquid, maybe, if it was just in a solution and it wasn't heated, you could write L next to it to indicate it's a liquid. But if it were like in our decomposition reactions, you would write water as a vapor or as a gas. So you have to indicate it differently. Solids, I think that makes sense. On weak acids, you write as molecules, so do not separate them out. So like you write it as C2H3O2 aqueous. That just means that you're not separating it. The couple that we had some problems with last week were sulfur 8, phosphorus 4, and carbon, and 50 wasn't actually one that I had from you guys last week. These are allotropes. They're just different forms of that particular element. So sulfur can be S or sulfur can be S8. Generally it's S8 because 8 sulfur atoms hang out together at all times. Phosphorus, the same story, 4 of them come together at all times. Carbon, this is actually a buckyball. Buckminster something ball. So that's a buckyball. Actually, I have an example of one in the back. But this is how carbon exists a lot of times within itself, 50 atoms together. So it's just another way to see it written in an equation. Don't be a little scared. What do I do this 8? Just believe it. Just write it as a subscript and you're good. Okay, so that's all background on reactions. You guys are going to watch 22 minutes of a YouTube video tonight to finish up reaction and basics, like types of reactions, and NIEs. Because in our next couple days, we're going to be starting a lab that's a 3-day lab on net ionic equations. And it's bits and pieces of it at a time. So that's what I need you to do tonight. I'm going to go through some of this this solution stoichiometry briefly, and then tell me if I need to do more, because after that, you guys can do your molarity problems that which you have in front of you. So a lot of this is going to be review because we just did some of this last week too. So quick review. Molarity is the big M. It is moles per liter. You see? Yes. This is a conversion factor. And if you can flip this conversion factor as you need to in a reaction stoichiometry kind of feel in a stoichiometry process. Another thing that I've mentioned to a lot of you guys last week is that anytime you have molarity, you can multiply it by the volume given, and it will be moles. And your goal is always to get to moles, so at least remember that. And that's because moles per liter times liters, cancel your liters, and you get moles. You can also work with millimoles and milliliters exactly the same way. So tell me how I would solve this problem. What's the molarity? So what am I looking for? What units? Moles per liter. So I'm looking for moles per liter. Made by dissolving this many grams of calcium chloride in enough water to make 475 mils of solution.
38.6 grams CaCl2 moles.
Okay, so take this calcium chloride, 2 moles. How?
By dividing by the atomic weight of CaCl.
Okay, so I'm just going to write that like here, okay? So we're going to have the atomic weight, so calcium plus, it's like 135, no, that's 40 plus 70, so it's like 110.
Yeah, it's like 100.
Okay, 110 grams. All right, so that's going to give us moles of calcium chloride, and then do what?
Then divide by 475 milliliters.
So we're just going to bounce that back. So then divide that by 0.475 liters. Moles over liters, molarity. I'm not solving this whole problem out. Not this one anyway. I will the next one. Well, let's talk about the rest of these. What volume? So what am I looking for? What unit? Liters. So always remind yourself that if you end up solving problems wrong, I'm going to make you do it my way. With no unknown question marks, givens, and stuff. It's more work, but you need to remind yourself what your question is. What volume of 3.67 molar aluminum chloride contains 2.5 grams of solute? What do I start with? Why am I starting with that and not the other one? Yes, good. This is a conversion factor. You don't start with molarity, you use it to get where you want, specifically because it's a fractional unit. All right, so 2.5 grams of aluminum chloride, do what? Get it to moles. Okay, so how do I get to moles? Okay, so 1 mole of aluminum chloride, 130-ish. Yeah, 127. I'm gonna go 130-ish. These molar masses are not correct. They're close though. Okay, so what's next? Okay, so what numbers go where?
It's 3.67.
Where does it go?
The bottom.
3.67 what? Moles.
Per 1 liter.
And per 1 liter. So it's okay to flip that conversion factor because it is just there as a tool for you, and then you're to liters in the end. You're good. So you just set up your skeleton if you need to. All right, how many moles of ammonium ions? This one's different. Ammonium ions are contained within that volume and this molarity.
Good.
So what's my question?
Moles.
Okay, so that's NH4 plus. Okay. What do I start with?
35, 16.
I like this. Okay, this is, I'm going to put of solution.
You can change that to liters.
Okay, so let me just go ahead and change that to liters. I'm a fan of millimoles, so you'll see in some of my answer keys millimoles. I keep writing moles. Okay, that's liters of solution. Okay, I can't do crap with this right now. What do I need to do? Use the what? Use the molarity to do what? All right, so I'm changing it to the moles of the whole shebang compound, right? So 0.39 or 639 moles of ammonium sulfide per 1 liter of solution. Okay, so the liters and liters of solution are gone. Now I'm here. Get me out of ammonium sulfide. Get me to where I want to be.
2 moles.
2 moles.
NH4 plus, right? Because I need to see the ions, right?
1 mole.
And that's called not really a mole ratio, but what have we been terming that? Internal mole ratio, right? All right, so that cancels out our moles of ammonium sulfide, and we can get to our moles there. I got one more that I know I need to do. I'll give you guys a second. Was printing next good for you?
Yes. Yes.
I'll kill trees for you, it's okay. Okay, so this is the, so we know how to calculate molarity, we know how to kind of toggle between volume, moles, and molarity. Now we need to know how to prep that solution. And there's a little tiny sheet that you picked up, like a little quarter sheet. That's our 20-minute activity that we're doing tomorrow on solution prep to make sure you know how to prep a solution like a volumetric flask, using acids or using solids or using liquids. So there are 2 versions of it. Did I print this part for you?
Yes.
Yes? Okay, good. So if I ask for you to prepare a solution from a solid, that means that you are starting with grams of that stuff. Okay, you're not starting with moles, you're not starting with the molarity given to you, you need to prep a solution from that. So you need to know 2 things. How many grams do you need, and what's the final volume final, that you need to prepare it to. So if you have grams, you need to then get some moles, and then you're going, I'm sorry, let me grab this from Jennifer. Come here, Jennifer. If you have things, I want this, and you can have you can do that. Just keep it for now. Keep it there.
Am I right on this?
Yes. Sorry, you could wait on this too. Or say that. Okay. If you know the molarity that you want, you need to multiply it by the volume to get to the moles of the solid that you also know that you're going to need. But you can't mass out in moles, you have to mass out in grams. So your next job is to get the grams of that solid. So I will always give you the molarity, and I will tell you your desired final volume. And then your job is to get to moles and then grams. Now what do you do with those grams though if you're preparing a solution? What are you going to mix them with? Water, okay? So add, certain number of grams to a volumetric flask with X amount of water, X milliliters of water, or liters of water, depending on what you're doing. So I'm going to show you one example here, but this is an explanation of what you're doing. You need to tell me you're adding 200 grams of sodium hydroxide to a 1 liter volumetric flask with X number of milliliters of water. And I'll give you an example there. That's if you're prepping from a masked out a previously solid compound. If I give you a stock solution, usually the stock solution is very concentrated, aka dangerous, aka like we don't use that in honors chemistry, we use weak stuff in honors chemistry. AP, we use more concentrated stuff. That means you're going to use the dilution equation, which you were familiar with in our last unit. So for this one, you would then take AM1V1, you would solve for whichever one is unknown. So it might say what volume of the stock solution is needed, for example, to make some sort of desired volume, a desired molar solution. So then what you would say is take X milliliters of stock solution and add to 1 liter volumetric flask until water at etched line. I'm going to show you a picture of that now because the volumetric flask, some people have used it and some people haven't, but the volumetric flasks are the best way to prepare solutions because they have an extremely accurate volume. So it's not like I'm 100 milliliters, it's like I'm 100.0000 milliliters. So we use them for solution prep all the time because they get us to more accurate solution concentrations. And you guys will use one of these tomorrow. So let's do 2 examples, one of each. From your prom set. Can we do from the prom set? Because I didn't do. Actually, I do have some, but I'm going to do. You guys start from your prom set. For those of you who need a picture here, though, I am going to tell you guys to look back here in just a second. For those of you who need a picture of what this looks like, this is a volumetric flask. It is a flask with a very, 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 very narrow neck. It has an etched line on it right here. You can see there's like an etching mark there. So whenever you are preparing your solutions, and you will tell me this tomorrow, you will say exactly to the T how you're going to prepare it. You're going to pour some amount of salt or your solid in here. You're going to then fill with water approximately halfway at first because you can't mix something if there's no space to mix it in. So you only want to fill it halfway. You can write on that. And if you fill it halfway, it gives you some swirling space. And then after that, you can add enough water to reach the etched line. Your meniscus should be at the etched line, not above or not below. So the bottom of the meniscus. At this point, you would then cap it and invert. And invert it just means to turn it upside down a couple times to make sure the solution is fully dissolved. So that's what a volumetric flask looks like from a, this is the preparation from a salt. If you had it from a liquid, same story. You would add the liquid here too. It's just easier to go ahead and add water because it doesn't need a whole lot of swirling space. But the only caveat is the safety rule, and this has been on the exam before, is how do you mix acids? The rule is you add acid to water. So if I'm diluting acid, you add acid. So just remember that. So that means I'm going to start off with a little water here, and then add acid and let it kind of mix, and then add the rest of the water. That's the only difference there. So add acid to water, just because you don't want acid splashing up on you whenever you have water. Whenever you add water to it at the end. Okay, I'm gonna let you guys. Start from your particular prom set, and I'll answer questions from there. I'll leave this up for you because I don't believe I printed this part. And it's got a good how-to step-by-step process if you want to take a picture of it or if you want to write it down. You guys see the prom set? It's going to be the very first thing on the staples packet. And I'm going to write 2 more things up here. In your procedures, you will be using the graduate pipettes for liquid stock solution. You will not pour it into a graduate center. That's on the picture.